And it's time for the 7th Avenue Project. More information at 7thavenueproject.com. Hello and welcome to the show. I'm Robert Polly. Today, an encore presentation, that's the term of art in this business, from 2009. My conversation with the theoretical physicist Leonard Susskind about black holes and their truly mind-scrambling implications for our understanding of physical reality. Just how weird are those implications? Well, consider this. According to one interpretation, if you fell into a black hole, you could wind up as dead as a doornail and alive and kicking at exactly the same time. Wrap your head around that one. And it could even be argued, thanks to black holes, that you and I are not really here at all where we think we are, but somewhere far out in space. Now, the person making these arguments for us today is not himself lost in space. Leonard Susskind is an eminently down-to-earth and practical guy. In fact, he was a plumber for a time. What's more practical than that? Before he became one of the world's leading theoretical physicists and a professor at Stanford University, though I understand he can still handle a plunger pretty well. He's considered one of the fathers of string theory, attempting to unify all the laws of nature, and has contributed to many other areas, including, of course, black hole physics, which was the subject of a long-running battle of ideas between himself and one Stephen Hawking. Leonard Susskind calls this difference of opinion the Black Hole War, which happens to be the title of his latest book. Here's Leonard Susskind. Leonard Susskind, welcome.
Thank you.
I thought I'd let someone more qualified than myself ask the first question.
Okay.
What is your beef with Stephen Hawking? It is jealousy, isn't it? It's time to come clean, Dr. Susskind.
Well, Stephen, yes, I am very, very jealous of you. Always have been. Your mind is just spectacular.
Nonetheless, you and Stephen Hawking had a disagreement starting, 20 or so years ago.
Yes, and of course it was a scientific disagreement. It was never a personal disagreement, and it was a disagreement over the principles of physics. It wasn't polemical. It had to do with what you trust, what a physicist should trust, whether the principles laid down by Einstein when he discussed how gravity works, or whether the principles that were laid down again by Einstein and Bohr when they discussed how quantum mechanics works. Which do you believe? Because they seemed to be coming into conflict with each other. In fact, it was Stephen very, very much who brought out that conflict and explained what that conflict was by asking a very, very powerful question. He didn't come to what I think any of us now think is the right answer, but by asking the question, I think he has created the stage for a revolution in physics.
What was the question and what was his answer?
Well, all right, so to put it briefly, the question was when information, and of course we would have to define very carefully what information means, but let's just say what you write down in a book or what an ordinary person means by information, when it falls into a black hole, is the information permanently lost to the outside?
And Stephen Hawking's answer was?
Stephen Hawking's answer was when anything falls into a black hole, it is gone. Now, that would have been okay. Things getting locked up inside a black hole, you might think is no worse than being locked up in a safe. You put your documents inside a safe and they're gone for the rest of the world. But then supposing the safe evaporated and disappeared, then what happened to the documents? What happened to the information that went in? That's what happens to a black hole. Given enough time, a black hole will evaporate. That was something that Stephen himself had figured out. And so there we had it. You put things into a black hole, you put information into a black hole, and you wait long enough, the black hole is gone, and according to Stephen, every little remnant of the information that ever fell into the black hole disappears out of our universe, and it's gone.
Well, before we get into black holes and how information does or doesn't disappear into them, let's just take an example, maybe a little closer to home.
Good.
There's a fireplace sitting over here.
Right.
I've got a copy of your book.
Right.
Let's assume.
Don't you dare.
Let's assume it's the only copy, and you've forgotten what you put in it, And I'm just going to light the fire and toss your book in there. Ashes to ashes, your book's gone. Now, I'm going to assert that the information in that book, seeing as you didn't make a backup on your hard drive,
Right.
You've forgotten what's in there, no one's read it, I'm going to say that information's gone forever.
Of course, for practical purposes, you're of course correct. But for fundamental physics questions, information never disappears. Where does it go? It goes into the smoke, it goes into the ashes, and if you had the capacity, or I had the capacity, to study every single molecule of the smoke, every single molecule in the ashes, and reconstruct, using the laws of physics, exactly how they got to be the way they were, or the way they are, you would find out that by running everything backward and reconstructing where things came from, you would reconstruct my book.
I could put Humpty Dumpty back together again.
You could put Humpty Dumpty back together again. That's a very fundamental principle of physics, that Humpty Dumpty is never so scrambled, he's never such a badly scrambled egg, that running the laws of physics backward could not reconstruct him.
Now, one thing surprises me about that. I mean, a couple hundred years ago, it was thought, and it was said by none other than Pierre-Simon Laplace, the great French physicist, that, if he knew the position and the velocity of every object in the universe,
Right.
that he could predict everything with infinite accuracy into the infinite future.
Right.
Just like watching billiard balls bump into each other.
Right.
And of course, you could run a film of billiard balls bumping into each other backwards and find out where they came from. But didn't quantum mechanics say that things are random? And doesn't that mean you can't predict?
Quantum mechanics is random and unpredictable in a very, very special kind of way. Here's an example. An electron goes through a little hole and comes out the other side. You look for the electron later and you find out that it's in a random, unpredictable position. That sounds like something very random happened. All right, but then you would expect, let's take that electron that goes through to the other side and then run it backward, reverse its motion and run it backward. Where will that electron show up? Well, it's very, very curious. The answer is that if you look at the electron before you start it going backward, you measure the electron, you do some damage to the system, and in so doing, you cannot reconstruct where it came from. But if you don't look at the electron, if you do nothing to it and just decide to suddenly run everything backward, that electron will come right back out of the original hole that it came from. So in the context of black holes, what it means is that after the black hole evaporates, if you take all of the products of the evaporation, photons, all the elementary particles that came out of that black hole, and without looking at them, without doing anything to them, you start them going backward, guess what? They will reassemble themselves into exactly not just the black hole, but eventually what made the black hole in the first place. That's the basic idea. It's a very, very fundamental principle of physics, that information is never lost. Everything depends on it. Everything we know about physics, energy conservation, momentum conservation, everything depends on that basic idea that nothing is ever lost.
Now, when did physicists start talking about information? I mean, a lot of us maybe think back to our school days and heard that energy is neither created nor destroyed.
Right.
But the word information might have applied to the contents of the textbook or what the teacher wanted to teach us, but physicists themselves didn't seem to me were talking about information.
Well, there was a pretty strong hint of it in the 19th century, in particular with the study of what's called statistical mechanics, gases and so forth. When the concept of entropy, it began to be understood in the late 1800s, particularly by Ludwig von Boltzmann, that what entropy is, the concept of entropy, what makes heat different than other kinds of energy, that entropy is simply hidden information. I don't think he particularly expressed it that way, but it's in his work. Entropy is information which is there, which you could extract if you simply had the capacity to look at every single molecule, but because there are so many of them, molecules that is, because there are so many of them, they're so tiny, and it's almost impossible to study the details, information gets lost, it gets hidden in the details, and that he understood eventually was what entropy really is.
Well, what is information? I mean, again, we think of physics as dealing with physical realities, matter, energy, forces, fields. Well, information sounds to me like something defined by human beings that's very subjective. If I scribble on this piece of paper and it means something to you, it's information. If you don't understand it, it's gobbledygook, it's not information. What's information to a physicist?
Yeah, that's what information means to a physicist is simply the distinctions that make one configuration of the world different than the other configuration of the world. So for simplicity, if we want it to be simple and we want it to think like Laplace was thinking, it's exactly what you said. The position and the velocity of every molecule. Really, it is the molecules. But if you wanted to write down that bit of information, no, not that bit of information, but the whole collection of information, you would write down all the numerical values of the position and velocity of every molecule. That would be the maximum amount of information that you could ever know about that system of molecules. But then the molecules might evolve for a while. You may get bored. You may decide not to look at them. Your eyes might get cloudy. You fall asleep. Whatever happens, and you lose track of a lot of them. Having lost track of them, you might say, well, I don't know nearly as much as I could have known. The difference between what you do know and what you could know is called entropy. And it's missing or hidden information or information that you are too lazy to keep track of.
Now, a lot of us have heard that entropy is disorder, that
Yes.
Things that are highly orderly, like a salt crystal, have very little entropy. Things that are really messy, like my bedroom, have a lot of entropy.
Right.
How does that square with your definition that entropy is hidden information?
Well, in your room, I bet you don't know where your socks are. The more disordered a thing is, the harder it is to follow, the harder it is to keep track of. So let's start with your case of the ice crystal, the perfect ice crystal. The perfect ice crystal is water at 0 degrees, 0 degrees absolute temperature. Right? Every single atom is in a very definite position in a crystal lattice. I could predict it for you, knowing enough about the physics of ice. I don't know enough about the physics of ice, but somebody knows enough about the physics of ice that they could predict for you where every single molecule was or is, just because they form a sort of checkerboard, very, very precise lattice.
And they have no choice. They're locked
They have
in
no
there.
choice.
0
They're
degrees
locked
of
in.
freedom.
There's no energy around that allows them to vibrate and to move around. Now you add some heat to it or some energy to it, and the molecules start to vibrate. They start to vibrate a little bit. You still pretty much know where they are, but then you heat it, and it goes through a transition where all of a sudden the molecules start sliding past each other. It becomes very disorderly. It becomes a liquid. It becomes a liquid. The liquid is very disorderly. The molecules are in random positions. It does not mean that you couldn't follow them in principle. It means that no ordinary macroscopic, large-scale measuring device is capable of keeping track of them. Just too hard. And so all of that detailed information about where all the molecules are is perhaps hidden is the wrong word. Perhaps just too hard to keep track of is the right word. Too hard to keep track of. You don't keep track of it. And because you don't keep track of it, you say there's entropy.
This is the 7th Avenue Project on Central Coast Public Radio, KUSP. I'm Robert Polly, and the topic today is black holes and how they've changed scientists' understanding of the universe. I'm talking to Leonard Susskind, theoretical physicist. His latest book is The Black Hole War. It recounts his 2-decade debate with Stephen Hawking about the nature of black holes. Well, let's get back to the black hole war, as you call it, and its beginnings. You first heard Stephen Hawking make his claim about black holes, the fact that information disappeared into black holes, in 1983, is that right?
Okay. My wife and I just had dinner with Stephen and his family in Cambridge. We were visiting him. And Stephen asked, I, of course, brought a copy of the book for him. and he asked me to read a little bit from it. So I read the first section of the book where I describe how he and I met in 1983. 3 or 4 minutes later, we hear from Stephen, I think it was 1981. And my wife looked at me and she said, yep, it was 1981. So I immediately called my publisher and I said, in the next round of these books, if they sell enough to have another round, please change it.
Well, was it though, in the attic of Werner Erhard,
that's correct.
Nay Jack Rosenberg?
Right.
That you first heard this claim by Stephen Hawking.
Absolutely.
At a gathering of physicists.
At a gathering of physicists.
Salon.
That included some extremely prominent, well-known physicists, Murray Gell-Mann among them. 3 particular people were there that were involved later in this controversy. Gerard 't Hooft, I'll call him Gerard 't Hooft. Gerard 't Hooft from Holland, who was, to my mind, the real inheritor of the mantle of Bohr and Einstein. To my mind, the greatest physicist alive.
Wow.
't Hooft, Stephen, and myself, and a whole bunch of other people. And we were all talking about elementary particles. We were talking about the theory of elementary particles, basically. Everybody gave a little talk. Stephen gave a little talk. And his talk was a bombshell, although nobody noticed except Gerard and myself. And he said, when information falls into a black hole, the details are completely obliterated. They are lost. Not like the case of the what we talked about, the fireplace, where the information really does come out in the smoke or up the chimney. There is no chimney to a black hole. And so Stephen said, since whatever falls into a black hole can never get out, and then the black hole evaporates, information is absolutely lost. Now, to 't Hooft and myself, this was something intolerable. We both felt very, very strongly that this so severely undermined the basic principles of physics that it had to be wrong. But we couldn't figure out why. Stephen had very much done his homework, meaning to say he had figured out or worked out all of the possibilities and had come to the conclusion that there was no alternative. A bit of information falls into the black hole evaporates, that bit is irreversibly lost for the outside world.
Now, I think to understand your counterattack, yours and Gerard 't Hooft's, did I say that right?
Yes. Well, in Holland he's known as Gerard. I'm not sure I said that quite right. In Italy, he's known as Gerardo.
Okay, but 't Hooft.
't Hooft.
Okay,
not 't Hooft.
Right.
't Hooft.
Right. Now, before we get into the counterattack by you two guys on Hawking's proposition, we need to back up and understand what a black hole is. And I'm just going to throw out a straw man for you.
Okay.
What I think is possibly the layperson's idea of what a black hole is. First of all, they're out there in space. They result from stars that collapse.
Right.
They run out of fuel. Their expansion stops. They collapse on themselves, and that the mass that forms, if it's heavy enough, if it's large enough, keeps pulling more and more matter into it until you get this super dense object.
Absolutely.
It's just solid matter. There's no longer the little space that you have, the vast amount of space you have between, say, an atom's nucleus and its electrons. Everything's packed in there as tightly as possible.
Right. Or as tightly as you can imagine.
Okay.
You might not have thought it was that possible.
Now, my image is of a kind of like rock in space that's super dense matter. It's got protons and neutrons and things in it, but they're all side by side, cheek by jowl. And it's got tremendous gravity such that everything gets sucked in, nothing can come out, including light.
Right. Well, those protons and neutrons eventually themselves get destroyed. The gravity of the black hole is so powerful that everything gets pulled into a concentrated, tiny, tiny point that's called the singularity. And the gravity, the forces near that singularity are so powerful that they would tear anything apart, including protons and neutrons. Anything that falls in will eventually get sucked to that very, very dangerous spot.
So that spot is where the real the matter that remains in whatever form is in the singularity.
Well, now that is, of course, what the controversy was about. Not quite as simple as that. Okay, so that was the simple picture of the black hole. That it is simply a point, almost a point of space of such concentrated dense material that the gravity is so strong that it would tear everything apart. But with that description, we've left out something very, very important called the horizon of the black hole. So let me try to explain to you what the horizon of a black hole is. Imagine Niagara Falls. All right, you're up on the river above the falls in your little rowboat. And you can only row so fast. I mean, you can row pretty fast, but only so fast. You row around, and eventually you come to a point as you go downstream where you can't outrow the current. Because if you look at Niagara River, you find out that it does move faster as you go downstream. And certainly as you go over the falls, it's moving really fast. At some point, that river is flowing faster than you can outrow. That's a point of no return. It's a point of no return where if you pass it, you are doomed. You're not dead, you're doomed. You wouldn't even notice anything very special. Everything is flowing with you, all the debris in the river, everything else. If you just look around, immediately around you, that river is flowing with you. You don't even notice that you passed the point of no return. The point of no return is the analog of the horizon of a black hole. And not only you can't outrow it, but a light beam can't outrow it. And so even your signals, as you're going downstream toward the center of the black hole, that point comes that you cannot escape. And even your light waves that you try to emit, you try to signal somebody on the outside with light, even that light gets pulled in. And so the horizon was where most of the contentious issues were. One view of the horizon, I've just explained, it's nothing special. It's just a point of no return.
It's a point where the gravity is so great that nothing can escape.
Yes, but you wouldn't notice anything as
Right.
you fell through the horizon.
Right.
You wouldn't notice it because it would be exactly like passing the point at which Niagara River is flowing faster than you can row.
Sure. In fact, it's only till you get to the bottom of the falls that...
Right, that's where you really get hit.
That's where you start to hurt, yeah.
But the fact of the matter is, the point where you're doomed
The brink.
is the point of no return.
Yes.
Right. So the horizon of the black hole, from one point of view, was nothing but the point of no return. And so somebody flowing past it, somebody falling into the black hole would notice nothing special there. Okay. On the other hand, there was another picture of the black hole that came later, and it had to do with quantum mechanics. It was Jacob Bekenstein who first realized it. What Bekenstein said is all the matter that falls onto the black hole forms a sort of coating around it, the coating at the horizon. It was known that if you stand outside the horizon and you watch material falling toward the horizon, because everything slows down because of the strange properties of time near the black hole, you will never get to see anything fall past the black hole horizon. You'll simply see it slow down, slow down, slow down, even though somebody else falling in will pass the black hole horizon. So what Bekenstein said is that the horizon of the black hole is made up of all of the bits of information that ever fell into the black hole. That's what quantum mechanics said. Very strange. One picture of the black hole, the horizon is nothing but a point of no return, and everything gets swept down into the singularity. The other picture, Bekenstein's picture, was the black hole horizon was where all of the stuff was stored.
Now you're going to have to explain that. If there's this thing at the center called a singularity with this massive and irresistible gravitational field, how is it that matter ends up way out at the horizon,
Well,
this shell that
that's
surrounds the singularity?
Think about this. For somebody outside the horizon, they can never see anything fall past the horizon. Why not? Because once it falls past the horizon,
Sure.
the light can't get out for you to see it. In fact, the time that it takes a light signal to escape from the near horizon gets longer and longer as an object falls towards the horizon. So you watching an object fall towards the horizon, it will seem to you that it takes forever for it to get there because the light gets so slowed down in trying to escape from the black hole.
So it never really even gets quite to the horizon.
It never,
from
your point of view, from your perspective outside the
Yeah.
black hole, watching it, it never gets to the horizon. All right? So now we had a conflict. One end of the conflict said all of the material, all of the matter, all of the information sort of gets stuck as it gets closer and closer to the horizon.
Oh, did you say it gets stuck, or did you say I just can't see it falling?
Well, if you can't see it, and then from your point of view, you're a physicist, you do experiments, you measure things, you can never see anything behind the horizon in principle. All of your measurements will say it got stuck. It got stuck at the horizon. And we're going to have to credit your statement because everything you do to measure what's going on will tell you that that stuff is stuck near the horizon. On the other hand, the poor fellow who fell through the horizon, he just never even noticed going past the horizon.
So we're talking in sort of post-Einsteinian terms where
Yeah.
there's no absolute privileged position from which to say this happened or that happened.
Exactly.
So when you have two conflicting perspectives like this, they're both true in a sense.
They may be both true.
They may be
of
both
course,
true.
it may be that one is false.
Okay.
But what we did find out in the end is that both are true. There was an element of this already in ordinary special relativity. Two flash bulbs go off, not at the same location, one far from the other. According to Newton and according to all physics which came before Einstein, there was an objective question: which flashbulb went off first? Either flashbulb A went off first, or flashbulb B went off first, or they went off simultaneously. No other possibilities. And what Einstein said is, no, that's not right. It depends on the state of motion of the observer. If the observer is moving in this way or that way, it may be that one goes off before the other, or vice versa. And Einstein unraveled it and thought very, very carefully about how you actually measure space and time and so forth. And it all turned out to be okay. That was right. He was right. There was no objectivity to the idea of which thing takes place first.
You are listening to the Seventh Avenue Project on KUSP Radio.
And we'll be back with more from theoretical physicist Leonard Susskind right after this. Now back to our interview with the theoretical physicist Leonard Susskind, originally broadcast in 2009. Leonard Susskind is the author of The Black Hole War, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics. So Bekenstein, you said, Jacob Bekenstein, established that, as odd as it sounds to say, this horizon that surrounds the singularity at the center of a black hole, we can say that's where the matter has sort of accumulated.
Now that is, of course, not exactly what Bekenstein said.
Okay.
What Bekenstein said was the capacity of the black hole to hold information. The number of bits of information that it could store was proportional to the area of the horizon.
Not the
internal volume.
Not to the volume of the black
Right.
hole where you'd think all that information
Right.
is sitting.
Right.
So if the horizon has all the information, it has all the stuff,
Right.
what's inside the horizon? What's down there below the
From
horizon?
the point of view of somebody outside the black hole, there is nothing. Everything that ever fell into the black hole, you should properly say fell onto the horizon, where it was stored in the form of hot bits of information which ultimately get radiated back out. That would be the picture from outside the black hole.
Yeah.
The picture for somebody falling into the black hole apparently is that there's nothing at the horizon. You just fall cleanly through and nothing happens to you until you get to the singularity. So this is one of these observer-dependent issues.
Two seemingly contradictory things
Yes.
are in fact both true, although it depends on the circumstances whether one seems to be the case or the other seems to be the case.
It depends on who's asking the question.
Who's asking the question?
Is the person falling into the black hole asking the question, or is the person on the outside asking the question? Now, we would get into a conflict if the person inside falling into the black hole could communicate to the outside. Then the outsider would have two conflicting pieces of information. On the one hand, he would have come to the conclusion that our poor observer, incidentally, the person who falls into the black hole is always called Alice. The person who stays outside is always called Bob.
In all physicist examples.
Right.
I thought you were going from Lewis Carroll with your Alice, but Bob wasn't in Alice in Wonderland, was he?
No, I don't know where the Alice and Bob originally came from. But poor Bob now has two conflicting pieces of information. He sees the bits of Alice come out in the Hawking radiation.
Oh, wait. Now you've just hit on my next question, which is, now, I'm hoping that listeners have stayed with us thus far and understand what we said about Bekenstein's findings, that the information in a black hole is in fact on the surface, that it is proportional to the area of the horizon, and so on. In a way, from the outside, all of the substance of the black hole is on this horizon and not inside of it.
This thin coating on the outside.
Right. And then the other thing you mentioned is that there is some kind of radiation, and it was discovered by Stephen Hawking. It's coming out of the black hole, something black holes weren't supposed to do. Something actually gets out of a black hole.
Well, now the question comes up, is it coming out of the black hole, or is it coming off this thin layer just above the horizon? All right? And I think it is proper to say that for somebody outside the black hole, they see this radiation being emitted from a region above the horizon, not coming from inside the horizon. Nothing ever comes from inside the horizon. But can we get back to Alice and Bob?
Yeah, let's go.
Okay, so Bob now has a conflicting situation. He's conflicted. He saw all these bits of information come out of the black hole. So he says, oh my goodness, poor Alice has been thermalized, boiled, cooked, roasted, turned into photons, and I see her photons come out. And I count them, and I see there's just enough of them to account for every bit of information that she originally had. My poor friend Alice is destroyed, and she was destroyed at the horizon, or just above it. On the other hand, he does another calculation. He says, I'm going to now be Einstein and follow Alice into the black hole using the general theory of relativity. And it seems to me the general theory of relativity says that the horizon was just a point of no return. Nothing bad happened to her there. Now, poor Alice, she's fine. She's fallen through the horizon, but she can't call out to Bob and say, I'm okay. So Bob will have to say, I saw it with my own eyes. I did the measurements. I detected all her bits coming out. The right story is that she was destroyed at the horizon. And there's Alice who says, with my own eyes, I see my hands, I see my feet, I see everything's okay. I know that I should have fallen through the horizon at 12 noon exactly, and I'm still okay. So, yes, that's right. There is this very, very conflicted situation. And this was the conflict in physicists' minds all during this period when nobody knew what to make out of it.
I think one little gap we should fill in at this point also is something you mentioned earlier, that black holes evaporate.
Yes.
Now, again, the old-fashioned idea that I had, the layperson's idea, is a black hole is something that's super compact, it sucks things in, nothing goes out, so how can it evaporate?
Yeah, that is the classical viewpoint, that nothing can ever get out of a black hole. But from one point of view, from Bob's point of view outside the black hole, that information never got into the black hole. So he sees it being radiated from above the horizon, from outside the horizon. He doesn't ever see anything come out from the horizon.
And what he's seeing radiating out from the black hole is what's known as Hawking radiation.
That's what's known as Hawking radiation, exactly. And that Hawking radiation carries off energy. Energy is mass, E equals mc squared. So that means it's carrying off the mass of the black hole. As the mass of the black hole is carried off by this radiation, the black hole shrinks and gets smaller and smaller and smaller, and eventually just disappears. So where are Alice's bits?
Exactly. Now, Stephen Hawking, of course, discovered Hawking radiation, but he thought that it didn't carry information, that it entered the black hole. He thought it was completely scrambled, yes?
That's right. He did not think of it as scrambled information. He thought of it as lost.
Mm-hmm.
Lost, completely lost inside the black hole.
Right. It goes into the blender, and
it goes into the blender and doesn't come back out. Just doesn't come back out because in order to get back out, it would have to outswim the current, and the current is flowing with the speed of light.
Sure. But per Bekenstein, if the stuff never really got into the black hole,
right,
if it stayed just above the horizon, then it's free to radiate back out.
Then it's free to radiate it back out.
Now, this took roughly 20 years to establish. This is what you call the black hole war, this disagreement, ultimately settled in your favor and Gerard Tuft's.
Well, I would say in some sense it was in everybody's favor.
Okay.
Stephen asked a very, very brilliant question. It was the right question at the right time.
Is information lost in a black hole?
Yes, and sorting it out, I think, has made a major change in physics. But yes, that's right. For 20 years, there was this conflict, which really was due to a false idea that a bit of information has to be someplace. It has to be at a definite place. Well, it's not at a definite place. Bob sees it one place, Alice sees it at another place. The idea that information is uniquely located in a definite place in space and time has gone the same way as simultaneity, that it was a wrong idea, that one event must occur before the other event or vice versa. And ultimately Einstein said, no, that's not right. There's an observer dependence about which thing happens first. Same thing here. There's an observer dependence about where a bit of information is located.
And I'm thinking back to your earlier explanation of information as residing in, for instance, the velocities and positions of atoms out there. You could call that information.
You could call it.
That has a place and a time, doesn't it? A definite place and time?
It depends on how carefully you look. The more and more precision that you try to bring to bear on where a particle is or where a bit of information is, the more you find it receding out to the boundaries of the universe.
Well.
Now we get to something that...
something else you're responsible for,
yes.
And that if we haven't already blown people's minds, probably will. And this is called the holographic principle?
This is called the holographic principle.
So this comes out to some extent, your work on black holes.
Yes.
And let's see if you can concisely state it.
All right. Let's go back to black holes for a minute.
Okay.
And this idea, incidentally, came not just from me, but even earlier from Tuft, the idea that the world is a hologram. But it started with the idea that the black hole horizon is a hologram. And here, ultimately, was the resolution of the confusion between Bob and Alice. You know what a hologram is?
Let's review that, actually.
So, an ordinary picture is a two-dimensional representation of something, and it really does not contain three-dimensional information. Its apparent three-dimensionality is in your head. The picture is two-dimensional. There's a picture of some flowers up on my wall over there, and I might be interested in what's behind the flowers. I can't go around the picture over to the side of the picture and take a look at what's behind the flowers. The three-dimensional information is really not there.
It's really just a flat surface.
It's really just a flat surface, and it does not contain three-dimensional information. So you might think that any two-dimensional film, photographic film or anything like that, can never contain three-dimensional information. But it's not true. Holograms are two-dimensional films, and if you look at them through a microscope, all you see is a bunch of random scratches, not really scratches, but random markings. You see nothing there, but they store three-dimensional information. And the way you reconstruct it is by shining light onto the hologram, and the light will reassemble itself into a three-dimensional figure. And in fact, you can go around to the back or look at it from the side or look at it from any direction, and you can make a hologram which really does contain the three-dimensional figure, so to speak.
We should say quickly how you make a hologram. You bounce a light off of an object, and you combine that light with light from what's called a reference beam.
Yeah.
And it creates what's called an interference pattern,
That's
where
right.
the two types of light come together, and their waves either interfere with or add to each other.
Yeah.
That is encoded on a film. When you shine another reference beam through that film, voila, you get this sort of projected three-dimensional image.
Right. And particularly, you could make a hologram, for example, of a model of the universe, a model of a whole bunch of stars, lots of them filling this room, for example. Mm-hmm. You could make a hologram of it, and that hologram would be a two-dimensional film. Mm-hmm. I call the hologram the film, the two-dimensional film. And then if you decoded the hologram, and that just means shine some light on it,
sure,
it would reassemble itself into the three-dimensional model of the universe.
Now, maybe that shouldn't be so shocking. I mean, you could write out an equation for me right now which would characterize a four-dimensional object or a five-dimensional object, and that would be five-dimensional information encoded in just a single line of text.
Well, you're right. You're right. So maybe it shouldn't be so shocking. But physicists had always thought there was something really invariant and special about the fact that information fills up space in a three-dimensional way. Mm-hmm. And so even when holograms were first discovered, it was rather remarkable and surprising. I was only 9 years old at the time. I don't remember it. But I think people were somewhat taken aback by the fact that a two-dimensional film could cast this really three-dimensional image.
Right.
Okay, so here then is the picture. There's the film, which is two-dimensional. There's the reconstruction, which is three-dimensional. Now go back to the black hole. The horizon of the black hole, or the region just above the horizon, is like the film.
It's flat.
It's flat. It's two-dimensional. It contains all this information. It's highly scrambled. If you look at it, you can't really see what it is without knowing how to decode it. On the other hand, what's falling into the black hole is like the image, the reconstructed image. So there's Alice. Alice is a hologram. Alice is the image. Which is Alice? Is she the scrambled up mess that's on the film, and which may be radiated off the film because the film is not inside the black hole? Or is she the image that's falling into the black hole, reconstructed, whole, and three-dimensional?
She's both.
Well, she's both. Both are equivalent. They're two different representations of the same thing. And this picture of information being holographic, being simultaneously three-dimensional and two-dimensional, is now a main theme of physics. It's not just in the context of black holes anymore. It came from black hole physics, but we now think the whole world is, in a sense, a hologram.
Why do you think that?
Well,
I mean, I understand how you could make that claim with regard to black holes, but
yes,
the rest of the universe?
Yes. All right. There are two ways to think about it. The first is, take all of the information in this room. Do we know that it's not in a black hole? No, we don't know that we're not in a black hole. This is the first fact. Perhaps there is a shell of material which is falling toward us that we can't see because it's moving with the speed of light toward us. Now, nobody really thinks this, but it's conceivable that there's a shell of material out there surrounding us that's moving toward us with the speed of light, and so we can't see it because light can't get to us from it. In that case, we are already inside a black hole formed by that shell of material. If we are already inside a black hole, then our image must be contained on a horizon which is way out there, far out, somewhere else. So that's one viewpoint, that we could be in a black hole. But there's a more mathematical viewpoint, and the more mathematical viewpoint was something which was derived partly from string theory, partly from thinking about black holes, which does say that there's a sense in which all information is stored on a two-dimensional film at a great distance. So this is something I am capable of explaining. But it takes a book to do it.
Well, let's take what I think must sound kooky to a lot of people.
Yeah.
And at least say, what advantage does that get you? If both the projection from this hologram and the holographic film are both real in a sense. We are the projection, the film may be out there and at the boundaries of the universe. What advantage is there in describing the universe this way?
Let's forget advantage. Let's talk about importance of it.
Okay.
Is this important for anything?
Yeah.
On the one hand, it satisfied the people's curiosity about how physics fits together properly, but it also may have some importance in several different ways. First of all, the combination of gravity and quantum mechanics, which was completely confused, and Stephen put his finger on what the confusion was, is probably important to our understanding of elementary particles. Elementary particles at the smallest possible distances are probably held together by something analogous or similar to gravitational forces. Mm-hmm. The world of elementary particles is ruled by quantum mechanics, but if particles are held together by gravity, that means that gravity and quantum mechanics have to be put together into a coherent intellectual framework. Stephen was pointing out that there was an apparent contradiction between them. Gravity and quantum mechanics did not appear to be able to coexist properly. His paradox, another way of saying it, was that gravity and quantum mechanics were in conflict with each other. So from the point of view of ultimately understanding elementary particles, we have to be able to understand how they fit together.
Quantum gravity.
Quantum gravity. So I think we've gotten that straighter than we had it before. And the other place where quantum mechanics and gravity come together is in cosmology. Cosmology, of course, is about the very, very big. But long in the past, the very big may have been a lot smaller.
The Big Bang.
The Big Bang. And most physicists believe that the Big Bang was a highly quantum mechanical event. So on the one hand, the ruling force of the universe is gravity. On the other hand, the creation of the universe was probably highly quantum mechanical. We're not going to get that right if we have misconceptions and wrong ideas about the way gravity and quantum mechanics fits together. So a lot of my work now is trying to understand what the implications of these ideas are for cosmology, for the origin of the universe, for the properties of the universe. There's a small number of people thinking about that. But the idea of the holographic principle has also had another life. The other life is in its applications. We've discovered an analogy between black holes and quantum mechanics and gravity in the form of quantum gravity on the one hand, and things which take place in, of all places, nuclear physics. When you collide together two nuclei at enough energy, you, of course, don't make a real black hole. You make a splash of energy that can be seen in laboratories. It's not a genuine black hole. But just like there's an analog between the solar system and atoms, there's an analog between black holes and what comes out of these collisions. That's being used. And the application very, very heavily uses this holographic idea. That the world is a kind of hologram, and that it can be analyzed as either, and now we're talking about the world of nuclear physics. It can be analyzed from either a three-dimensional point of view or a two-dimensional point of view, and sometimes the less obvious way of thinking about it wins and gives you better information. So the holographic principle, to put it in short form, the holographic principle is rapidly becoming a tool for rather ordinary purposes that was totally unexpected, certainly unexpected by me.
You're listening to KUSP. The show is the Seventh Avenue Project. I'm the host, Robert Polly, and my guest today is physicist Leonard Susskind. The subject du jour, black holes. It's also the subject of Leonard Susskind's most recent book called The Black Hole War. Now, I'm always thinking about the layperson's point of view, since that's who I mostly talk to.
Right.
And I'm wondering about a possible confusion between, or an attachment to, an idea of sort of literal reality versus useful descriptions or models of reality or representations. Now, when we talk about the universe as a holographic projection, out there is some distant film running, and we are its three-dimensional projection. Should we take that literally, or should we say, oh, that's a useful, potentially mathematically valid way of describing certain phenomena, just the way a graph is a good way of looking at, say, population growth. But we would never confuse that graph for the population of the United States, literally.
Yeah. I would have to say I'm ambivalent about it, frankly. I don't know how to answer that question because I think our brains were simply not constructed to understand reality with a capital R. They were constructed in order to understand stones and rocks and flowing water or whatever. They were not built to understand this world of abstract mathematics. They were not built to understand the very, very difficult, unvisualizable world of modern physics. And so I'm not sure what exactly you ask when you ask, is it really this or is it really that? I think what you're asking is about mental pictures rather than actual reality. Actual reality is the facts. The fact is that the number of bits of information that can be stored in a room is proportional to the area of the walls of the room, not the volume of the room. The fact is that our best mathematical descriptions of what takes place in a world with both gravity and quantum mechanics is in terms of what's going on the walls, meaning the film, meaning the hologram. Which is real, the image or the hologram, or the film itself? Which is real? I think physicists have learned not to use the word real and not to use the word reality. It gets us very confused.
I want to go back to one thing that I think might be troubling some people listening to this conversation. We said that, and you just said it again, that information is on the boundaries. You know, the information in this room could be said to be on the walls of the room. When we talk about the universe, where is that boundary?
That is a subject of present debate and present confusion and present argument. One view of it, and it's a view I like, the universe has a horizon itself. The universe is almost like an inside-out black hole. Because everything is moving away from everything else.
The universe is expanding.
The universe is expanding, but it's expanding even faster than we thought. Mm-hmm. It's called accelerated expansion. If you go out far enough, everything is moving away from us faster than the speed of light. That means that we are sort of in the interior of something that the exterior of is almost like a black hole.
Things are receding away from us so fast we can't see them.
We can't see
them.
Beyond
this horizon, right. All is invisible.
Right. That's a cosmic horizon. Mm-hmm. It's not a black hole horizon. Mm-hmm. But the mathematics of a cosmic horizon are very similar to the mathematics of a black hole horizon. And so one answer to it is everything is stored out there on the boundary of space, which is the cosmic horizon. And we know the cosmic horizon is there. We even know how far away it is.
And, of course, its location depends on where you are.
It depends on where you are, but how far away it is from you may not depend on where you are. Uh-huh. If you stand at sea level, no matter who you are or no matter what you are, and you're 6 feet tall, the horizon is about 3 miles away. Mm-hmm. On the other hand, if you move from one place to another, the horizon moves. That's right.
Right. Now you say that though you may have been the victor in this argument with Stephen Hawking, that you salute him as having raised these really important questions, and you go back to a paper of his from 1975 called "Particle Production by Black Holes," where he talks about Hawking radiation.
Yes,
and you say that by the time the repercussions of that paper are fully understood, physicists will recognize it as the beginning of a great scientific revolution.
I believe that's the case.
What is this revolution we're talking about?
Well, the revolution we're talking about is understanding space, time, matter, and information. And that means, and that's everything. There is nothing but that. Understanding how quantum mechanics fits together with gravity. Ultimately, I believe that will be important in understanding the origin of the universe, elementary particles, So I can't think of anything that it doesn't bear on.
It's really interesting because you sometimes read that there was a bit of concern in fundamental physics that maybe some of the greatest discoveries have been made and things have stagnated since the standard model of particle physics was really, really confirmed 30 or so years ago, and that things have sort of not developed since then. And you're saying a whole new revolution was instigated about 30 years ago by Hawking and others.
Yes, and it's been an ongoing revolution which has been changing rapidly. No, the problem is the enormous difficulty of getting direct experimental confirmation of these things. It's very, very hard. We're getting information from cosmology. We will be getting new information about elementary particle physics, but we're talking about worlds which are so remote that all we can do is get the littlest fragment of information, and from that we have to put together the right picture with knowing so little. The ideas have not been stagnant. I would say the revolution in ideas about how physics works has been faster than any time I can ever remember, or any time that I know about in history. The ability to confirm these ideas by direct experiment has gotten exceedingly hard. Why? You have to build monster big machines to create accelerators to see elementary particles, and you have to create monster big telescopes to see the heavens, and it just gets harder and harder and harder. Mm-hmm. Nevertheless, I'm quite optimistic.
Lastly, you say of yourself that at the outset of this this contest of ideas with Stephen Hawking, which was quite some time ago and nobody could have known the outcome, but you said you had no doubt that you would eventually prevail.
Certainly by 1993, 1994, I was absolutely certain, yes. Before that, I was pretty certain. In 1981, when I first heard it, I was extremely puzzled. I really felt Stephen could not possibly be right, but on the other hand, how could he possibly be wrong? I was just completely confused.
What would have gone by the wayside if Hawking had been right?
Our understanding of energy. Our understanding of energy flows through the understanding of information. If information is not conserved, there is no reason for energy to be conserved. All of our understanding of the laws of physics, every law of physics that we know and understand, fundamental law, is a law about how information is transmuted from one form to another, but never lost. So I would say the entire 300-year history of physics would at best be very confused.
Thus the subtitle of your book, My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics.
Right.
Well, thanks for making the world a safer place.
You're welcome.
I'm Robert Polly. This has been the Seventh Avenue Project. More information and audio of past shows can be yours at seventheavenueproject.com. And before I go, I'd like to clear up something I said back at the beginning when introducing the show. Here's what I said. According to one interpretation, if you fell into a black hole, you could wind up as dead as a doornail and alive and kicking at exactly the same time. Now that part about exactly the same time, not quite right. Because as Einstein showed us, there is no master clock that the whole universe runs on. Time changes depending on the frame of reference, and in the alive-dead paradox that I was talking about, where the person falling into the black hole is alive and well inside the hole, but dead to those outside, well, those are two very different frames of reference. So it doesn't really make sense to talk about synchronicity. In fact, ordinary sense doesn't apply at all in this case, but sometimes when common sense falters, poetry steps up. And the situation reminds me of those immortal lines from the great John Shade. He wrote, I was the shadow of the waxwing slain by the false azure in the window pane. I was the smudge of ashen fluff, and I lived on, flew on,